Hey everybody, let's give this op-amp problem a try. So this one is not ideal, right? Because already it says there's some input resistance and output resistance, open loop gain, all that stuff. So basically, the insides of this op-amp will look something like, I'll draw it big. Okay, so for this coming in, there's going to be an input resistance here between these two pins. So then this is where that 16K resistor is. And then the 240K resistor is over here. And then that goes to this input. All right. So this is the input resistance, which it said is here, 560K. All right. And then there's an output resistance and an open loop gain. So the open loop gain means there's some voltage dependent voltage source inside, or there's some gain, this open loop gain A, and then time, and then it's a function of this is the non-inverting input and the inverting input. So the voltage from here to here is our VN, and then from here to here is VP. So VP minus VN, right, is this voltage right here. So it's this gain, which is 50,000. So 50,000 times the difference between here and here. Okay. And then that goes like this out. And this is the output resistance, which is 8K. 8K right there. Okay, and then the rest of the circuit, there's this 200K feedback resistor this way. And this output resistance here, or the load, sorry. Load resistor. Okay, and that's where we're trying to find the output over here. Okay, so let me label some of these nodes. So if I call this N over here, and I'll call this over here P, and this can be my output node. All right, so let's write KCL at this node N. KCL at node N. All right, so let's go this way to the left. So Vn minus 0 over 16K. Now let's go this way toward the right. So let's go from here all the way to over here. So that would be Vn minus Vg, right, from here to here, over 560 plus 240 is 800. Okay, and then let's go this way. So Vn minus Vo over 200K. All right, so we have one equation. Now let's write KCL for node O. Right, let me make a little bit of space. Okay, so for node O, this will be a second equation. Okay, so let's go this way. Vo minus Vn over 200K. Then let's go this way. Vo minus 0 over 20K. Now let's go toward the left. VO minus the voltage sitting right here, which is this. A times VP minus VN over 8K. Okay, so let's take a look at what we know. So we have this node voltage, this node voltage, this one, this one. Okay, so we have VO, VN. We have 3 unknowns, but only 2 equations. So we're going to need another equation. And already, look, we need some kind of expression for VP, the voltage here. And notice that, see this resistor and this resistor? Maybe let me draw it vertically. So see, there's node N, and then node P, and then the VG over here, right? So you see how this is a voltage divider, right? So just from here to here. So from here to here, that would be Vn minus Vg. From here to here would be Vp minus Vg. So let's just write an expression for this one right here. So this is a voltage divider. All right, so I'm talking about right here. Vp minus Vg is this. Let me see what the numbers are. 560K, 240K. Okay, so the voltage from here to here would be this resistor over this plus this. So that would be 800 times the voltage from here to here, right? So this whole thing, which would be Vn minus Vg. Okay, so if we just move this on that side, then we have an expression for Vp. Can I just do that? Like that, right? So now we have an expression for Vp, which this can go right there. Okay, so why don't I just write that immediately? So if I combine equations 2 and 3, then we have VO minus Vn over 200K plus VO over 20K plus VO minus A, which, what was A? 50,000. 50,000. Or right here. Times VP, or here, which is all of this, 240 over 800, Vn minus Vg, plus Vg, is this, right? Minus Vn. We're over here now. Okay. All of that divided by 8K equals 0. Okay, so now I'll call this equation 4, maybe. So now let's take a look at our unknowns. Let's see. And then for this particular problem, we're saying that Vg is 1 volt. Right, so this is actually known. So that we only have so recap, right? I combined equations 2 and 3 to get equation 4. So now if we look at equation 4 and equation 1, that's just 2 equations, 2 unknowns. Right? So just solve one of them, whichever one for Vn. Let's say this one, right? Solve this for Vn in terms of VO, and then plug it in here. And then you have an expression for the output voltage. Okay, and then once you have that, then you have all three node voltages, right, this one, and all these two. And then once you have those two, you can solve everything else, right? We'll have this, that's the output. Right, oh, it's right, we'll solve those two. Once you know VO, the output voltage, you plug that value in here, and then you can solve for VN. And then once you know VN, you plug it in here, and you have VP. So now you have all three. So now you have this, this, and this. And then if you know VN and VP, just subtract one from the other, and that's part C. And then if you know VP over here, and you know VG over here, then you can get the current here, right? It's just VG minus VP over 240K will be the current here. All right, and then let's do this. If we try that again, but let's say this is an ideal op-amp. So if I say if this is N, this is P, and this is my output, then if I write KCL at node N, okay, then going this way, Vn minus 0 over 16K plus going this way, Vn minus Vo over 200K, and then going this way is some current IN equals 0. And then for an ideal op-amp, the voltage here equals the voltage here. Vn equals Vp, and the current going this way is 0, which means this is 0. The current going this way is 0. So if the current going this way is 0, that means there's no voltage difference between here and here. Right? So then the voltage here, Vp, is the same as the voltage here, Vg. So let me write that down. Vp equals Vg. Okay, so then see how this just goes right there. And then we're saying Vg is 1, so 1 over 16K, 1 minus Vo, that's 0. And there we go, just solve for Vo, right? You can equals 0, move this on that side, multiply everything by 200K. There, so VO equals 200 over 16 plus 1. And you can simplify that, but that's it, right? Okay, so give this a try. I kind of skipped some of the punching numbers in the calculator, but I just wanted to go over the method to solve this. Okay, so hopefully that was helpful. I'll see you on the next video.